some graph that you want to forbid, then you have a lower bound on Ramsay numbers. So this is how you should use the theorem, how you should read the theorem. If you can find an F-free lambda, if you can find a pseudo-random graph, then I give you a lower bound on Ramsay numbers. And when do I give you a better lower bound? I give you a better lower bound if the graph that you found me was better. Namely, if lambda is small and d is large. So this is our theorem. It has, as I said, a one-line proof. And a consequence of this theorem is all the things that I've said. And in fact, I promised you the proof. So here's the proof. So the theorem says, if you have an ND lambda graph, I can find you a Ramsay graph. We need one fact, which is non-trivial, but not very complicated. It follows from the expander mixing lemma. It's a fact proved by Alon and Rödel in 2003 or so. It says that if you have an ND lambda graph, then the number of independent sets of size t is at most lambda to the t. So this is a non-trivial upper bound on the number of independent sets. And that's the only fact you need in order to prove this lower bound. So how do we prove this lower bound? We basically take this ND lambda graph and we choose a random subset of vertices by picking each vertex independently with probability 1 over lambda. So what you start with a big graph, this ND lambda graph on n vertices. After you take this random choices, essentially you're flipping a coin for every point, heads with probability 1 over lambda. It's in your set if you get heads. You end up with a set of size n over lambda, which is exactly the right-hand side in this theorem. So if you look at the subgraph induced by those vertices that I've picked, the n over lambda points, then essentially there's no independent sets left in that subgraph because the number of independent sets was so small. The chance that an independent set falls inside that subgraph is essentially 1 over lambda to the t. And the number of independent sets is lambda to the t, so the expected number is 1. So essentially there's no independent sets. You can delete a vertex for every independent set. So the induced subgraph on that vertex set S is a Ramsay graph with this property. And then if you plug in the right ND lambda graph, you get all the bounds that I've been speaking about in this talk. So that's how the main theorem, as I said, it really is one line. So if you plug in the best known constructions for odd cycle pseudo-random graphs, you immediately get this theorem that I claim. If you plug in the constructions for, if you plug in the best known conjectures for cliques, you get this main theorem in Ramsay theory that I stated. Of course, we don't know these constructions exist, but they're conjectured to exist. Okay, and the last thing I want to do before I finish is some open problems. So what are the open problems? Well, there's one main open problem. The main open problem is to construct optimal F-free ND lambda graphs. And I've indicated that you can use ideas in number theory, you can use ideas in coding theory, you can use ideas in group theory, you can use ideas in finite geometries in order to make these constructions. And I think with the correct confluence of all these ideas, one may be able to do these things. And that would be very surprising, prove that they don't exist. One can also extend this theory or think about extending this theory to hypergraphs. So here, instead of edges having being sets of size 2, edges are going to be sets of size 3, okay? And the theory is much more complicated, but it's fairly well developed at this stage. And we have some things that are similar to graphs, and one could try to do this. But at this point, we have no theorem similar to what I stated for hypergraphs. And another thing you could do is you could try to obtain explicit constructions of Ramsay graphs using these methods. So our constructions require far fewer random bits than the previously known probabilistic constructions. So maybe you can make them actually explicit, which would solve another long-standing open problem in Ramsay theory, namely to construct these Ramsay graphs explicitly. So there's a lot to be done, but I guess the main message, the theme of this talk is that perhaps these pseudo-random graphs are more important than Ramsay graphs. And hopefully that's the message that you've gotten, and that's all I have. So thank you very much for your attention.
Thank you. Any questions from the audience? Please unmute yourself and ask. Can I ask a quick question?
Go ahead.
Mr. Mubay?
Yeah.
Some years back, David Zuckerman and student Chattopadhyay had work on two source extractors construction connected to Ramsay graph constructions. It's kind of sounded similar to the construction of expanders implying Ramsay graphs. So do you have any comments on that?
Well, so I think that they are looking at it more from the complexity point of view. So they have the best known constructions for lower, so-called explicit constructions for lower bounds for the diagonal Ramsay number. But I think the approach that I'm using is rather different. They are sort of, so theirs is more theoretical computer science construction, where the definition of explicit is that there's an algorithm that you can use to construct it. Whereas what I'm proposing is some mathematical object that we know exists, and just to use that object and immediately find the Ramsay graph inside that object. Indeed, that is the best known construction, but I'm proposing something that's slightly different, I think.
Okay. Because there's been a lot of work in that field connecting different pseudo-random objects to each other. Construction of optimal codes to extractors, expanders, and so on. They're all interconnected with some changes in parameters.
Yeah.
So is it possible to randomly sample deregular graphs which are free of KS, the S clicks, and say something about the lambda that you will get? Is it like?
Yeah. So I mean, if you randomly take a deregular, so exactly. So how do you randomly sample a graph that does not contain some fixed subgraph? In fact, this constrained random processes that I've, this 45-page paper, this 1/4 in the R3T is precisely doing this. It's a random greedy algorithm where you make sure you don't contain the fixed graph at each step in the process. But the analysis is very tricky. And what I've tried to indicate in this talk is that you don't get optimal results potentially using that method. But using this bigger, more complicated, richer pseudo-random structure, you can just find what you want inside it all over the place.
Because for random deregular graphs, we know by Alon Millman's theorem that lambda is about square root of d, theta of square root of d.
But the density is not enough. The density is not enough.
Okay. Are there any other questions?
Okay.
If there are no other questions, maybe I don't see any raised hands. It was a wonderful talk. Thank you so much. Okay, maybe we should stop now, no? Because is there a... Okay.
Thank you, Arvind and Dhruv Mumbai, for their excellent talk. So we'll break for about 5 minutes, and the same link is working. So
okay,
no change to switch the link.
Okay.
Vijay.
Yes.
It's Peter. I just want to make sure I can share screen and so on. How do I do it?
Okay.
Good morning.
Yes, Swami. ബാലുവിന്റെ അവിടെ കറണ്ട് പോയി. ഞാൻ റെഡിയായി വെച്ചിട്ടുണ്ട്. കറണ്ട് വന്നാൽ പുള്ളി ഓഫ് ആൻഡ് ആയിട്ട് പറയാൻ പറ്റും. ഇല്ലെങ്കിൽ ഞാൻ റെഡിയാണ്.
Okay, thanks. I've been made co-host. Thanks. You see that? Can you see that?
Yes.
Okay, great. Then I'll just leave it like that. Let me make sure that that I have all the pages. Okay, so I'm here. I'm ready when you tell me to start.
Okay. Thank you.
Thank you.
Okay. Yeah, we will start in about 2-3 minutes.
Yeah, okay, I'm ready. Thanks.
Professor Balasubramaniam, who is supposed to chair this session, is not able to join due to some technical hitch.
Okay.
So I am privileged to chair this session, and I'll be happy to read out a brief profile of Professor Peter SARNAK, who is a professor in the Institute of Advanced Study, Princeton, US from 2007 onwards. And he is a PhD from Stanford University. And among the several awards and honors that he has received, the most recent one was in 2019, Sylvester Medal of Royal Society. And he is among the trustees of MSRI and Committee of Fields Medal Committee, Chair Shaw Prize in Mathematical Sciences, and also Scientific Advisory Committee of the Fields Institute, and the editorial boards of several journals. And above all, he has guided more than 50 students for PhD, including Kannan Soundararajan and Akshay Venkatesh. In fact, I came across a talk about an announcement of a talk by Peter SARNAK in Cambridge University on a similar problem of gap sets. So, and I requested him to give this lecture here. And I suppose that this is the content of the lecture is same as that I expected. So I welcome Peter SARNAK for his talk. Thank you.
Thank you, Vijay. Thank you very much for the invitation. And in these Zoom talks, please feel free to interrupt anybody, because otherwise you sort of feel like you're just lecturing in a sterile way. So I always interact, and I encourage anybody to ask questions. Well, it's a great pleasure to talk at this conference on number theory and discrete math. In fact, as was mentioned, I chose a topic which I think fits quite squarely with this, as well as with Ramanujan, who we are celebrating. And so let me get to the topic. And except for a few slides, everything should be quite elementary in terms of understanding. I'll have 2 slides which are a little more advanced and go through them quickly. So don't worry if that's not material that many of you are familiar with. All right, so I want to talk about joint work with a young applied physicist, Alicia Collar at the University of Maryland, and Fan Wei, who was a member at the Institute for Advanced Study, a postdoc last year, and is now at Princeton University as an instructor. I'll explain what we are doing in a minute. So the setting is very much familiar to this audience, I believe, especially with Dhruv's talk, which introduces my talk quite nicely. Thanks. I will talk only about 3 regular graphs. So this is the only way I communicate with you other than talking and the slides and this cursor, which I hope you see. So 3 regular, every vertex has 3 edges coming out of it. All graphs are finite, connected. They may or may not be planar. This one's planar, this one's not. The second one is what's called a Ramanujan graph, and obviously I'm going to spend a little bit of time on Ramanujan, so I'll explain that in a second. A very desired graph from many points of view. I was very happy to see Dhruv mention that they give explicit examples of graphs with a large chromatic number and large girth, a problem that, as he pointed out, Erdos invented the probabilistic method, counting method, to produce just in terms of counting, but one uses, as he said, algebra, algebraic geometry, finite geometries to make constructions. And it's a fact that in algebra or these kind of constructions, there's either a formula, this is my kind of meta statement, that there's either structure or randomness, and when there's randomness, then these arithmetic things try to mimic random, and that's why they can be very useful. All right, so everything will be 3 regular graphs, and the interest will be in large 3 regular graphs. Small ones, one can search for them, and they're very special, but we'll be interested in large ones. The spectrum, as in the title, so let's make sure we're all on the same page. So capital X is the set of all 3 finite 3 regular connected graphs. Sigma for Y, for such a graph, Y, sigma Y is going to be its spectrum. So we have a matrix, adjacency matrix, which is, I like to think in terms of Laplacians, more geometrically a little bit. A applied to a function, the function's a function from the vertices to the complex numbers, and you sum all nearest neighbors according to the graph of f of y. So if f is a constant, because I'm 3 regular, I'll get 3 times what I started off with. So 3 is always an eigenvalue. It's always simple because the graph's connected, and it's an easy exercise to check that -3 is an eigenvalue of this matrix A, or is in the spectrum, and simple if it's there, if and only if the graph is bipartite. So those are the only 2 easy numbers to immediately recognize in the spectrum, and they are very informative in terms of connectivity and bipartiteness. And this lecture is about what other gaps can you create in the spectrum for large Y's. So we're going to be taking bigger and bigger members in Y and try create a gap in some part of -3, 3. And in a way, I have been studying this for many years without actually formulating this very clean question, but it somehow gelled in recent times because different fields were asking for this kind of thing. Now, the most celebrated gap is the gap that Dhruv mentioned, the Alon-Bopana gap. That is, if you have a sequence of 3 regular graphs whose size gets larger and larger, you can never make the spectrum lie in a bigger interval than 2 root 2. 2 root 2 is less than 3, by the way. In 2 root 2, 3. That interval is a maximal interval that is free of eigenvalues. So there's they didn't know if there's an infinite sequence of graphs which has no eigenvalues in that interval, but what they showed, and there were reasons they wanted it, and Dhruv mentioned some of those, and the word expanders were mentioned. This gap measures how good an expander the graph is, which is a very desirable feature. So this was the maximal gap possible there. And so that is the first answer to our question, what gaps can you create? And the remarkable thing is you can create an infinite sequence of graphs which are so gapped. And these are what, as Dhruv said, we did call, Lubotsky, Phillips, and I constructed this in 86, 87. Margulis, who was still in Russia, independently constructed variants of these in around the same time. And they were constructed, and as we constructed them, they depended on the Ramanujan conjectures. So we call them Ramanujan Graphs. And this part of Ramanujan's work is one of the many great influences he had on mathematics. But to me, who works in maybe more mainstream number theory, this was very influential. He made a conjecture about the Ramanujan tau function, as it's called, about how big the coefficients, which were later shown by Hecker to be the same as eigenvalues of certain Hecker operators. He recognized the extreme, the biggest they could be. He had applications as to why he wanted these bounds. That's not often mentioned as much. And the remarkable thing is that the proof of the Ramanujan conjecture that he formulated, his exact problem, took much of a good chunk of great 20th century mathematics, including the Weil conjectures as formulated by Weil, the connection between the Weil conjectures and the modular forms and the Hecker eigenvalues. So the Weil conjectures are in arithmetic geometry over finite fields. And then, of course, the proof of the Weil conjectures by my colleague Deline. So Deline is the person who proved the Ramanujan conjecture for the Ramanujan tau function and many, many other ones. And this particular construction of these graphs makes use of a special case of the Ramanujan conjecture. In fact, you only need Weil's proof of the Riemann hypothesis for curves over finite fields. So as you can hear from all the words I'm saying, it uses a lot of different tools and a tremendous impact by Ramanujan in formulating and understanding its importance. And in fact, his interest in it was for maybe number theory, not combinatorics, but it's got this very similar effect. When I used to give lectures in the 80s, I would say that these graphs will never be constructed by any other means other than through Ramanujan's ideas in number theory. But one should never say such things because a few years ago, Marcus Spielman and Srivastava gave a construction using interlacing polynomials and double covers, computer science type construction. But what replaces the Riemann hypothesis is the Li-Yang theorem in statistical physics, which puts zeros of certain polynomials on a circle. So in a way, no direct connection, but there is this construction, and this is quite remarkable. Though it doesn't construct the non-bipartite Ramanujan graph, and that remains a major open, so that hasn't matched number theory. Okay, I think you heard a little bit about this, but expanders, this big gap is very important because it produces expander graphs, which are extremely useful and are really fundamental in many aspects of computer science, complexity, constructions of codes, and many, many other things. That's the gap at the top. So, and now I'll move away. That's a fantastic story. The gap at the top, it gives those graphs with large girth and chromatic number, the non-bipartite ones, that is, which probabilistic, at least this interlacing is never achieved, as I just said. Alicia Collows, an applied physicist, came with some problems in tight binding Hamiltonians, asked me some questions, and we started to work with this with her colleagues. And the big question for us in that particular project was, what gap can you create at the bottom, at -3? In chemistry and large clusters, so-called Fullerenes, one tries to create a gap at 0. So once one is trying to create gaps for large 3 regular graphs at different parts between -3 and 3, you may as well ask the general question, what gaps can you create? Is this, how rich are 3 regular graphs? And that's the question I want to address. But the answer at -3 is worth a number of slides. It's really beautiful. So what gap can you create at -3? So if you have a 3 regular graph, you could take its line graph, which you just construct by taking each edge, putting a vertex in the middle, and then take the graph sorry, you take the edges, make those the vertices, and you join two edges if they have a vertex in common, and that's called the line graph. And then because the adjacency matrix can be realized in terms of the incidence matrix, and this, which is a not necessarily square matrix, and you have the matrix, the incident matrix, call it B, and B times B transpose, and B transpose times B have relation in their spectrum. You get that the spectrum of the line graph of any graph consists of the number -2 to the multiplicity, the number of edges minus the number of vertices, together with the spectrum of the following operator, minus twice identity, plus adjacency, plus the diagonal matrix of the original graph, where the diagonal matrix has entries which are the degree of the vertices down the diagonal. So there's a very clean relation which we'll be using between the spectrum of a line graph and the spectrum of the original graph Z. But since this is easily seen to be a non-negative matrix, the spectrum of any line graph always starts at -2. So you see, if we take a line graph, we're going to automatically be able to make a gap. Nothing will be below -2. And since by the variational principle that you teach of how you compute eigenvalues of a symmetric matrix, the minimum eigenvalue is a minimum of the quadratic form X transpose AX over XX with the usual inner product on the vertices. So it follows that if you have any induced subgraph of a given graph, that from this variational characterization, so you're working over a smaller variational problem, that the minimum eigenvalue of a graph Z is less than or equal to the minimum eigenvalue of an induced subgraph B. And so if you want to characterize all graphs which have the spectrum starting at -2, they cannot contain pretty much any small graph that you write down, if it has, especially if it, in particular, if it has lambda min B less than -2. So Hoffman recognized this feature, and we'll call these Hoffman graphs. And one could try classify these Hoffman graphs, graphs which have for the adjacency matrix, have the spectrum starting at -2 and to the right. And this was achieved in an absolutely beautiful paper by Cameron, Goethals, Seidel, and Schult in 1975 called Line Graphs, Root Systems, and Elliptic Geometry, where they characterize basically, so we saw that if you take a line graph, you basically will get a graph whose spectrum starts at -2, and they prove the converse except for some variants of line graphs and some finite number of sporadic graphs connected to root systems, E8 lattice, and angles between vectors inside the E8 lattice. I highly recommend this beautiful paper. We'll be using it. And that's this characterization I just told you of graphs whose spectrum starts at -2 and to the right for, and that's not just for 3 regular, but we'll apply it to 3 regular. So this sort of forces us to make the following construction. If we start with a graph which is 3 regular, and we make its line graph, sorry, we first divide the graph. I was just, it's early in the morning for me. I've got my order a little wrong here. So we first subdivide my 3 regular graph by taking the edges and putting a vertex in the middle of each edge. That subdivision gives me a 2-3 regular graph. I then take the line graph of that, and I will get back a 3 regular graph if you think about it for 2 seconds. And so this construction, which I'll call T, which takes me from 3 regular graphs to 3 regular graphs, and sews in basically at each vertex a 3 regular triangle, just a triangle in each, so we call it the triangle map, increases the number of vertices by a factor of 3 and keeps the graph connected. And because of that relation in the spectrum, we can compute in terms of some nonlinear transformation, the spectrum of T of X in terms of X. And that will be very useful to construct gaps. So using the theorem of Cameron et al., we were able to show, this is just a simple application of the theorem, but it's important for us here, so let me state it, that if you have a 3 regular graph and its spectrum is contained in -2, 3, in other words, you've created a gap at the bottom between -3 and -2, you can only do this if you are in the image of this triangle sewing map, if you're large. So except for finitely many exceptions, if you're large here, we characterize the image of T in terms of the spectrum, and this tells us everything we want to know about the maximal gap. This is a maximal gap. So the Alon-Bopana gap is at the top. This is the maximal gap at the bottom, and is very much cleaner because it's actually characterizing anything which achieves this maximal gap. So back to my question. What kind of, so the general question is, we have a closed subset of -3, 3. We'll call it spectral if there are infinitely many 3 regular graphs whose spectrum is contained in that set K. The complement of a spectral set is a gap set, and we want to make small spectral sets or maximal gap sets, just like there was at the top and the bottom. What can we do? And that's the question I want to address. All right, so here are my 2 slides that are a little more setting is a little more advanced. Let me start with, they all concern locally symmetric spaces. So like a flat torus, here's a flat torus in the middle where I join, so it's a Riemannian space, which is flat, just a part of the plane, and I join opposite sides to get a flat torus, and I compute the spectrum of the Laplacian, which you can write down explicitly. And if you let this torus, let's say its area is 1, but you let it degenerate, you'll find you can never create gaps. If you let the volume get large, you also can't create gaps. So the spectrum of flat tori, when you do the analog problem of large locally flat tori, so you make them bigger and bigger, you can't create gaps. The situation is very different in hyperbolic surfaces. It's, you take the up-off plane. This is a place where Ramanujan worked and Hardy with him, but they looked at holomorphic functions and maybe even mock modular functions. Today we have things called weakly harmonic forms, which are connected to Ramanujan's work. But there's a completely full theory there of eigenvalues of Laplacians, which is not something they considered, but which was considered by Maas and Selberg and people like that. And there are basic questions about the gap in the spectrum there, and these go by the name of the Selberg eigenvalue conjecture, something that's really fundamental, and is, I normally call this the Ramanujan-Selberg conjectures, because they are conjectures in the theory of automorphic forms, and probably, to me, the most important problems in the theory of automorphic forms concern the Ramanujan conjectures. All right, what's that got to do with creating gaps? So there is a beautiful feature here that if you're in a higher rank locally symmetric space, so S is a Riemannian symmetric space, or a Brouwer-Titz building if you want to make it combinatorial, and you're in a higher rank, then there's this beautiful theorem of these 7 authors, they call themselves the seven samurai, which say that you fix your symmetric space of higher rank, you have a quotient which is something like the graph we're talking about. So it's a lattice in the space of isometries. This is another topic that is well represented in India, thanks to Raghunathan and his school, the rigidity and higher rank and arithmeticity. Anyway, the rigidity feature that I want to explain here is due to these 7 authors, that as the volume of these locally symmetric spaces of higher rank grows, you could ask what spectrums, what gaps you can create in the spectra of these locally symmetric spaces. So just think of them as very fancy graphs. And there's an amazing theorem of this, of these 7 people, which say that there's nothing that can really happen that's exotic, in the sense that these locally symmetric space, Binyamini-Schramm, converge to the universal cover. In the case of graphs, it would mean 3 regular graphs. It would mean these 3 regular graphs want to converge to the universal cover, which is the 3 regular tree in this Binyamini-Schramm sense. Now, what the Binyamini-Schramm convergence means is that they're converging not at every point. So it's not true that every point looks locally like the universal cover, but the random points looks like the universal cover. And if that's true, the spectra of the local objects must converge to the spectra of the universal cover. And in that sense, the spectrum of the universal cover was computed incidentally by another Indian mathematician, Harishchandra, in this setting. And those are well known, and there are no gaps that can be created. So this is what I call very rigid. No gaps, in higher rank. In the context of algebra, finite fields, coding theory, there's a beautiful theorem of Ladut and Sfassmann, which is, and a very recent paper of Serre. Serre is still very active, he's over 90. And it's very similar to the question I'm asking here about graphs. So this is my last fancy slide. Suppose you look at a curve over a finite field or an abelian variety of a finite field. It's a theorem of André Weil, that the eigenvalues of the Frobenius acting on cohomology, say the field is fixed, Q, the genus of the curve is going to get large. The eigenvalues of Frobenius are of modulus square root Q. That's this Riemann hypothesis in finite fields. If the genus of the curve is G, there are two G eigenvalues. They lie on the circle of radius square root Q. Because of bilinear relations, the eigenvalues are symmetric on the circle. And you could ask, as you take the genus to infinity, Q is fixed, where can these eigenvalues place themselves? Can you create a gap? And the theorem of Sfassmann and Ladut, in connection with showing that Goppa codes have a certain limited property, but very impressive in terms of their coding properties, is that no matter how you choose your curves of larger and larger genus over the finite field, you can never create gaps here. On the other hand, for abelian varieties, which are much more general than curves over the finite field, Serre recently answers this question, and he shows that if you have a compact subset of the circle and you try to create all the eigenvalues to lie inside that subset by an infinite sequence of abelian varieties over the finite field with larger and larger dimension, then you can do that essentially if and only if the transfinite diameter of this closed set of the circle is at least Q to the quarter. I'm going to define transfinite diameter right now. The transfinite diameter of a circle radius square root Q is square root Q. So the set K has to have transfinite diameter, or it's the same thing, capacity, Q to the quarter, somewhat smaller, but we go from a very rigid situation that you can't create gaps if you eigenvalues of a curve, but you can if you eigenvalues of a abelian variety, but there's one constraint, and the constraint has to do with transfinite diameter. What is this transfinite diameter? So in Facketer in 1930 proved a beautiful theorem, which we'll be using, and which Serre, of course, used there, and a converse to this theorem as well. And that is, if you have a compact subset in the plane, so this is, now we're back to basic statements, not necessarily easy proofs, but basic statements. If you have a compact subset in the plane, and suppose you ask about all the algebraic integers which lie inside the set, as well as all their Galois conjugates, should also lie in the compact set. So you ask, can I arrange there to be more and more algebraic integers and all their Galois conjugates lying in this compact set? And the theorem is that if the transfinite diameter of K is less than 1, then there are only finitely many such algebraic integers. Quite beautiful theorem. Polya and Sago extended it. What is this transfinite diameter, which is a measure of the size of a set? It's not the Lebesgue measure, but it's a potential theoretic definition. But the simplest definition is just the geometric mean. So if I take n points in this compact set K, and I take the maximum of the geometric mean of the distances between the points and call that dn, then it's very easy to see that dn is a decreasing sequence as I increase n, and the decreasing sequence converges to a number, and that number is called the transfinite diameter, and it's also called the capacity. And there are many ways of identifying this number. It's not completely, it's not that easy to compute for general Ks, but it's an important invariant, and it's decisive in our problem, as you'll see in a second. Okay, so now back to our question. And I think I have still about 17 minutes. So I'm now going to describe what Alicia Collar and I can do on this problem. I've described the gap at the top and the gap at the bottom. And now we're going to look at gaps anyway. So the question is, can we create gaps? Are we in a rigid or are we in a fluid situation? And the upshot of what I'm going to tell you is that three regular graphs are extremely rich. They show both fluid and rigid features. So the first theorem we prove is, can you create a gap at any point? That is, can you find, given any point C in -3, 3, of course you can't create, 3 is always in the spectrum. -3 as we've seen, we can isolate it, but let's take any point in the closed interval -3, starting closed at -3 and open at 3. And can we find an open neighborhood about such a point, such that, and an infinite sequence of three regular graphs, so that the spectrum of the three regular graphs does not meet the interval? In other words, can you gap? So in practice, if you wanted to create three regular graphs which don't have an eigenvalue near a given point, can you arrange that with larger and larger three regular graphs? And our first theorem, which is uses the techniques, especially that map T and a number of other things, is that yes. And not only can you do that, but you can do it with planar graphs. And proving this theorem with planar graphs was quite a bit more difficult. Ramanujan graphs or expander graphs can never be gapped at 3. That's the definition, essentially, of an expander. That is, and it's a theorem of Taj, and well, it's a min-cut theorem, but a short version is due to Lipton and Taj, which shows that planar graphs cannot be gapped at 3. So Ramanujan graphs cannot be planar. I think I might have said that the wrong way. If I did, I apologize. Anyway. So with planar graphs, you can't gap at 3, but we're not saying we're gapping at 3. If you take a point slightly less than 3, we'll be creating a very tiny neighborhood about there. So it's kind of subtle. So that's the one, that's the good news. We can gap any point. What general constraints are there on a gap set? So the first theorem is that a gap set, a spectral set, remember, we're trying to make small spectral sets, can never have capacity less than 1. And that you can imagine uses Feketa's theorem, and it's not difficult from Feketa's theorem. And then quite a bit more difficult theorem that we prove, and you'll see why we prove it, is that a spectral set, remember a spectral set is a set for which there's an infinite sequence of graphs. It's a closed subset of -3, 3, for which is an infinite sequence of graphs whose spectrum is contained in there. It must meet every interval of which is bigger, or has length bigger than 2. So you cannot create a gap set which is bigger than width 2. This took us a while to even understand that such a thing is true. And the remarkable thing is we can find such planar gap sets. So you can find an infinite sequence of 3 regular graphs. I'll show them to you right now, which is gapped at -1, 1, that's got length 2, and also at -2, 0. And we don't know any other interval of length 2 that can be gapped. So we don't have a complete understanding of this problem. It's quite tricky, but we do understand these gaps at 0. So we understand the gap at the top, the gap at the bottom, and now in the middle, we also have the maximal gapped interval. Here is the actual picture of the gap. So this is an infinite sequence of 3 regular graphs. There's something periodic except at the end. So as you can see, the way it's cut off here and at the top, keeping it planar is a little different to all the other points. And here it's eigenvalues. Of course, we prove that there's no eigenvalues between -1 and 1, even as no matter how many vertices you put down in 3 regular graphs. So that's a demonstration, just like Ramanujan graphs showed that the Alon-Bopana interval actually can be realized, and Dave showed it was maximal. Here we have both sides of the story. -1, 1 is the maximal possible gap set, and here this realizes a maximal gap interval. And this is a little more complicated, realizes with a planar graph, but it's actually got loop multiple edges here. We don't know if we can actually make it planar for the gap -2 to 0, which is also length 2, and here the eigenvalues computed numerically. But as I say, we have a proof that these graphs do not have any eigenvalues in there. All right, I want to show that the capacity was also optimal. So remember, we have this triangle map, which took me from 3 regular graphs to 3 regular graphs. And I indicated a relation between the spectrum of a graph and its line graph, and then the spectrum of a graph and a subdivision graph is also quite simple. And if you combine those two operations, you get a very simple formula, and it's extremely important to us, for the spectrum of the triangle. So if I start off with a 3 regular graph Y and I apply the triangle map, I get a graph with 3 times more vertices, and I compute its spectrum. It's the inverse image of the spectrum of Y together with 0 with multiplicity n over 2. N has to be even if you're 3 regular graph, the number of vertices. And so it throws in the eigenvalue 0 and -2 with high multiplicity. And F is this nonlinear quadratic polynomial, which we're going to only look at on taking real values. So for example, if I apply F -1 of -3, 3, I'll get the 2 to 1, this map, I'll get the interval -2, 0, 1, 3. And if I apply it again, I'll get to divide that in a Cantor-like set construction. So if I keep on dividing, taking inverse images, I get a closed subset of -3, 3, I'll call it lambda. It's a Cantor set. And the orbits, this is very important in our proof and in what follows. So this is the quadratic map in question. And I'm showing to you that if I start with a random point here and start iterating F, it'll run off to infinity. But there's this Cantor set, it's also called the Julius set for this rational map, which is invariant, which I'm calling lambda. And that Cantor set is very important for us. So this, if you restrict our map, which is that quadratic map, to this Cantor set, which is invariant, it's topologically, as a topological dynamical system, it's just a shift on the 0, 1 to the n space. It's very chaotic. So the action of F on lambdas, not simple at all, and that's kind of important for us. But what is the most relevant for us is if you take the set A, which is this closed Cantor set, together with the inverse images of 0, once inverse image F1, inverse F -2, F -3, and so on. You take the union of all those points. Turns out all these points condense, they accumulate only on lambda. So that this set A here happens to be a closed set because these are isolated points. And the only accumulation points are the Cantor set lambda. So this set is a fat set because of lambda in terms of, say, its capacity. But it's very small in terms of this because this is a countable set. So it turns out that the capacity of A is 1. And remember that there was a constraint that a spectral set must have capacity greater or equal to 1. So this set A, remarkably, is a spectral set. And it has to be minimal, and we prove it's not only in terms of capacity, but it's genuinely minimal. There is no smaller closed set which can carry the spectrum of an infinite sequence of 3 regular graphs. So A is the smallest set in terms of capacity that we know, and it can't be smaller in terms of capacity from the Fullerenes theorem. But it's a remarkable set for which there's an infinite sequence of 3 regular graphs, all of whose spectrum is contained in K. And in fact, it's more structured than that, thanks to Cameron et al.'s theorem, used eventually. If you have an infinite sequence, or if you have a very large graph, let me say, we have this map T, which takes me from 3 regular graphs to 3 regular graphs. And if you start with something whose spectrum is in A and you apply T, it won't change. And there are only finitely many orbits, T orbits, of 3 regular graphs whose spectrum is contained in A. So that is the other side of the coin. So we've constructed these maximal gaps in the middle. And I could summarize it like this. What do we know about maximal intervals that can be created? So at the top, we had the Alon-Bopana, realized by Ramanujan Graphs. Here are 2 planar examples that I gave you with interval length 2, which is the biggest the interval gap can be. And at the bottom, we have the example of -3, -2, the Hoffman graphs. So those are maximal intervals. I don't know any other ones. Minimal spectral sets, which means I'm allowed to be more than an interval. We have this remarkable set A, which has capacity 1 and is absolutely minimal and is realized by planar. And then we have the non-bipartite Ramanujan graphs, my favorite right now, because only Ramanujan's ideas can achieve them. And that is, we don't have -3, so all the eigenvalues lie between -2√2. This is a non-bipartite Ramanujan graph by definition. All the eigenvalues lie between -2√2 and +2√2, together with 3, which is always an eigenvalue. I still have 7 minutes, is that correct? Is anybody there? Hello?
Yeah, it's 7 minutes.
Yeah, okay. I got a little panic that I'm just talking to myself. Okay, thought maybe I'm disconnected or something. Okay, great. That's fine. So this summarizes sort of what we know explicitly. Of course, by Zorn's lemma, you know that there have to be these minimal spectral sets or maximal gap sets. We have these constraints and we have these explicit solutions. I want to add about this example here, which is on the top, on the left here. These cannot be realized by planar graphs. That was the fact that an expander cannot be, so these are expanders, they cannot be planar. But much more, what's very interesting here is Hebert, Glasner, and Virag. Hebert was part of that 7 samurai team, have proved the converse here, that if you have a sequence of non-bipartite Ramanujan graphs, so they have all their spectrum contained in -2√2, 2√2, of course, together with 3, then they must Binyamini Shram converge to the tree. So it's a converse. So the only way you could ever create Ramanujan graphs is you start to look more and more locally like the 3 regular tree. Of course, if the girth gets large, you, of course, look locally like the 3 regular tree. And the remarkable theorem is they don't put any condition on the girth, and you still must converge to the 3 regular tree in the Binyamini Shram sense. So it's a beautiful theorem. It's a converse. And what it shows is that you cannot create any more gaps. So if you a sequence of Ramanujan graphs, you could never create a gap inside -2√2 and 2√2. So this is not contained by the Alon-Bopana theorem at all. Alon-Bopana is just about this interval over there. And as you know, we can create a gap between -3, and there can be nothing between -3 and -2√2, which is part of the proper definition of Ramanujan. But within this interval, you can't create any more gaps. So this set is truly a minimal spectral set. It's the smallest. But there, of course, what we're showing is the theory is very rich. This is the minimal spectral set. There's no smaller spectral set, but if you start and want to make a gap somewhere else, there's other minimal spectral sets. So this is what we know about that story. And I just want to end in the last 5 minutes in adding to the case of Fullerenes, which I find to be quite attractive. So firstly, you could ask, you start adding conditions on your graph to see at what point can you no longer create gaps. So at what point do they start to rigidify? Well, putting the condition of planar by our first theorem does not prevent you from creating gaps anywhere. But what does create that is if you are planar, then you could ask about the faces. Now a planar graph has a realization and essentially unique in terms of faces. 3 regular graphs. So you have a 3 regular graph, and you could limit the number of faces in the sides of your realization. So let me call F36, of course the definition could be generalized, to be all the 3 regular graphs which have at most 6 sides per face. Well, Fullerene is a 3 regular graph connected, which has at most, all of these are planar, as I'm saying, that's how I can talk about faces. There are 3 regular graphs which have at most not only 6 sides per face, but have only 5 or 6 sides per face. That's the definition of a Fullerene. So we put the condition on the graph that it's a either F36 or Fullerene, and then we ask, can you still create gaps, or what gaps can you create? By the way, here's what Fullerenes look like. So Fullerene has only hexagons, And by Euler's formula, just by simple writing down Euler's formula, you'll find that there are exactly 12 pentagons. So here's, they're all planar, they're all on the sphere, and the blue ones are the pentagons. And all these are examples of Fullerenes. Here the pentagons are on the two edges. These are called nanotubes. So what kind of gaps can you create? And that's a basic question that I find quite attractive. I don't know that it's so basic when the Fullerene becomes so large, which is what we're asking, because usually people like the buckyball and things like that. But mathematically, this is a lovely question. What gap, have you rigidified the story? And here's our theorem. So this is joint with fan way as well. So for F36, if you're lying at most 6 sides per face, then you do rigidify to a large extent. It's not true. You can still create a gap, and you can create that gap minus 1, 1. And in fact, that picture that I showed you there earlier was an example of an F36. So that sequence shows that you can gap minus 1, 1. But the remarkable thing is that's the biggest and that's the unique maximal gap. So unlike 3 regular graphs where this picture is very rich and complicated, here it's very simple. This is the unique maximal gap. That is to say that if you have a sequence of planar F36s with number of vertices going to infinity, the spectrum must become dense outside of minus 1, 1. And you can realize minus 1, 1 with a sequence. So the answer is very clean for F36. For Fullerenes, we're busy writing it up. It's quite a bit more complicated in that there's 2 intervals and there's a number in the middle there that you can't remove. So it's a similar kind of story. You can create this gap. These numbers are algebraic numbers. And the point in between here, there will always be an eigenvalue with some multiplicity there. But creating Fullerenes is kind of tricky because you have to put these 12 pentagons somewhere. And we can do that. And the pictures, what I'm saying here, this is the maximal, unique maximal gap. And we have one other theorem in terms of this rigidity question, sorry. And that is, at what point with the number of faces do you stop being able to create gaps at any point? So we show that if you allow yourself many faces, sides per face, so not 6, but 64, then you can gap any point. And we believe that already at 7, you can gap any point, but we only can do this at 64. So in other words, this number 6, the hexagons, are very important in terms of rigidification. All right, I don't think I have time to describe any of the proofs, I'm afraid, so at least I got to state what we do, to mention Ramanujan, and I will be happy to take any questions. Thank you very much.
Any questions from the audience, please?
And just to be clear, we have Carla and I have a paper on the archive where you will see the details of how we prove these, because I didn't go into any of these. The proofs are mainly elementary constructions and combinatorial constructions to show that gaps can't be bigger. You actually construct approximate eigenfunctions combinatorially just by the fact that there are many vertices and 3 regular. So the deepest gap is still the gap that comes from Ramanujan.
Sorry. I have a question, sorry. Thanks. This is Mahesh Kakte. Peter, thanks for the nice talk.
Thank you.
I have a question. At the end, you mentioned these numbers that appear for gaps for Fullerenes are algebraic numbers. So what sort of algebraic numbers are these? Do you know anything about the degree, for instance?
Yeah, it's low degree. It just comes from solving some equations which are connected with, okay, so let me explain what the difficulty is. So if you, so you first have to, the sort of main theorem is that if you have an Fullerene, then there are going to be the 5 pentagons, and mostly you have hexagons all over the show, as you can see. And so the point is that you first show that infinite, if you have a growing sequence of Fullerenes, there must be some part of this graph which converges to a quotient of the hexagonal lattice, which is the whole planar version of this without the pentagons. So it's some quotient. These are quotients. These nanotubes are quotients of that divided by the isometry group there, or the hexagonal group is just basically translations and a finite extension of them. So you will look like a neighborhood of one of these here, and then you have to, so then we compute the spectrum of these quotients. We go through that and compute them, and they are given by these algebraic numbers that I'm telling you about. And the hard part is then we have this infinite, we want to make a planar thing. So we have a tube like this, and I want to cap it off with 6 pentagons on each side. That happens to be a very tricky question. Mm-hmm. And certain of these nanotubes can't be capped and other ones can. And we have to find the ones which we can cap with this interval. And there's an eigenvalue that appears in this capping from a calculation, spectral calculation, and that's that number, and it is algebraic, and its degree is small. Okay. I can't remember the number.
Yeah, thanks.
By the way, there is a beautiful unsolved question for Fullerenes, and that is from Huckle. The reason Fullerene, there's this chemistry way of trying to guess the spectra of these kind of clusters, which is called Huckle Theory. And what becomes important is the gap in the middle of the spectrum. So there's an even number, Fullerene has an even number of eigenvalues. And you look at the midpoint, at the 2 middle eigenvalues, and can you create a gap between the 2 middle eigenvalues and still allow the number of vertices to go to infinity? And we don't know the answer to that. We've been trying to do that, and I think that's a really beautiful question. So when I say that we're creating gaps, we first fix the point, we first fix the interval, and then we try to create a gap. If you don't know where this midpoint is going to be, and it moves on you, and we don't know how to do that. And I would love to see the answer to that. And that is really probably the real chemistry ideal question. Is it true that you can, that gap is the stability gap, at least for small Fullerenes? Can that gap be kept open, or does it have to collapse? I don't know.
So these Fullerenes are just C60 or generalized Fullerenes?
I've just been looking at the genuine definition of Fullerenes. If you take any kind of generalization, then it becomes much easier. So for example, if you allow a little impurity like F36, so this is an example. This is a beautiful example, this one. You see, this is this capping that we did that was very successful. So you have here triangles. It's not, everything here is hexagons except for the triangles here and the outside triangle. So if you allow a little impurity like that or other generalizations of Fullerenes, you give yourself a lot more freedom to answer these questions. But I haven't studied those in great detail. I've taken this as a mathematical problem. Fullerene or F36, yeah.
Okay, if there are no other questions, let us thank Peter for his excellent talk. Thank you.
Thank you.
The next session starts at 7 o'clock. Plenary lecture by Professor George Andrews. It's the same link, so you can relax for 5 minutes, 5 to 10 minutes. Okay.
Hello?
Thank you for joining.
Yes, fortunately, everything is working now. I will need to share my screen.
Okay. Arvind login ചെയ്തിട്ടുണ്ടോ നോക്കണേ. പോവാ. ഇല്ല, പുള്ളിയുടെ കാര്യം നോക്ക്. പുള്ളിക്ക് ഷെയർ ചെയ്യാൻ.
So I am not able to share yet. It says that the sharing is disabled. There it is. Okay.
Now you can do.
Yes. Okay.
Is it okay for you?
Yes, it's okay. I can now get. All right. Okay, that's good. So how much time do I have for my talk?
5 minutes.
How many?
Or you can start in about 1 or 2 minutes.
So it's an hour, you say?
45,
or is it 45 minutes?
45 minutes.
45 minutes, thank you.
Arvind ഇതാക്കായിരുന്നു അല്ലേ? റെഡിയാണോ?
Vijay? Vijay, can you hear me?
Yeah, I can hear you. You can start now.
Okay. Very happy to introduce Professor George Andrews. He did his PhD from the University of Pennsylvania in 1964. He has been the faculty member at Pennsylvania State University since 1964, where he is currently the Evan Pugh Professor in Mathematics. Professor Andrews is well known for his work in number theory, especially his work on partitions. His long-term interest in Ramanujan's work is very well known, including his work on his last notebook. Professor Andrews has received numerous awards through his career and has served on numerous editorial boards of math journals. Now over to Professor Andrews. Is he there?
Okay. All right. Thank you very much. Thanks to the Ramanujan Mathematical Society. Thanks to the Rajagiri School of Engineering and Technology. I'm honored to be able to participate in this event honoring the memory of Srinivasa Ramanujan. The talk that I want to give is probably best presented by my actually working through what I'm going to talk about. So that's why I'm sharing the screen using my iPad. one of the things that has of most interest in the lost notebook of Ramanujan are the Mach theta functions. The Mach theta functions have been known for 100 years now because Ramanujan, in his last letter to G.H. Hardy, wrote that he had behaved in ways near the natural boundary for them, in ways that were very similar to the classical theta functions, but he believed these were actually not theta functions. A natural question to raise is, why would anybody think that there was another class of functions that were very much like theta functions, but not theta functions? What would give anyone the idea of that? What even would give someone of the talent of Ramanujan the idea that that is the case? So at various times since discovering the lost notebook, I have speculated about how Ramanujan thought about things, as well as others have done. Often I have been incorrect. And so what I say this morning may well not be how Ramanujan discovered the Mach theta functions, but I want to at least describe a plausible Sorry about that. All right, so this is about how Ramanujan may have discovered the Mach theta functions. And I hope everybody can see what I'm writing. These functions are quite mysterious, and so why Ramanujan would have even dreamed that they were possible is something that I would like at least to give a plausible idea of what actually might have happened. So Ramanujan was very good at dealing with what he called Eulerian series, or what are now called Q series, or basic hypergeometric functions. And one of the things that he was good at was utilizing a famous summation theorem that goes back to Cauchy and probably beyond, although Ramanujan may well have found it for himself. And the theorem is this: the summation n greater than or equal to 0 of 1 minus a 1 minus a q dot 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 1 minus a q to the n minus 1 t to the n divided by 1 minus q squared to 1 minus q to the n equals to an infinite product n equals 0 to infinity of 1 minus a t q to the n divided by 1 minus t q to the n. This is a fairly elementary result. All one does is to try to expand the infinite product in a power series involving t, and a very simple functional equation allows you to compute the coefficients. For simplicity, I'm going to use classical notation, which is namely this sort of expression. I want to not have to write out these products every time. So I'm going to write a semicolon q sub n for these products, so that this series becomes a q sub n t to the n over q sub n equals a t q infinity divided by t q infinity. There are a number of nice applications of this. Actually, while this series probably dates from the 19th century, Euler knew a number of special cases, and in particular, Euler knew the following special cases. Summation n greater than or equal to 0. What happens when a is equal to 0? 1 over t q infinity. And another limiting case, which I will write as follows: summation n q to the n squared t to the n divided by q sub n equals minus t q squared infinity. Both of these are corollaries of this result. So what I want to take you through next, because this is one of the simpler things that one can do with these series, and something that Ramanujan was completely familiar with. If you look at many of the formulas that appear in the Lost Notebook, this sort of theorem it permeates many of the identities that he found. And so let me write this. This originally goes back to Heine, and I don't know that it appears explicitly in the Lost Notebook, but numerous special cases of it exists, so that Ramanujan certainly would have known how to prove this. So this is the summation n greater than or equal to 0. It has several of these products in it. And what it involves is relating this to another series of the same sort with a concomitant infinite series, basically multiplying times a transformed series. And now this times the summation n greater than or equal to 0 of c over b q sub n t q sub n b to the nth power q sub n a t q sub n. So this is Heine's a Heine's series, and various special cases of this appear explicitly in Ramanujan's Lost Notebook. But I want to take you through the proof of this, because Ramanujan quite clearly knew this method of proof inside and out, and this is probably is most revelatory of how he would have searched, how he would have happened on the Mach theta functions. So the proof relies on the following idea. A q sub n equals, let me write it out now so that you can see how it goes. 1 minus a q to the n minus 1. So what you can do is to rewrite this as a quotient of two infinite products. So you take this and you write it all the way out, and just goes on forever. And in the denominator, you cancel out the terms that you don't want, so that you have precisely that finite product in the numerator. So this is a q infinity divided by a q to the n q infinity. So here's the way Ramanujan, here's the way Heine, here's the way anybody who proves this result would prove it. You take the summation n greater than or equal to 0, a q sub n, b q sub n, t to the n, divided by these two products. And what you do is you look at these two quotients and you write each of those finite products as a quotient of two infinite products. So you leave the a and the first two things the same, leave this explicitly there. And now you rewrite this as c q infinity, c q to the n q infinity, b q infinity, b q to the n q infinity. Now you see two of the infinite products do not involve n at all, and so you can bring them out front. And summation n greater than or equal to 0, the first terms stay exactly as they were. And these terms, this expression is a quotient of two infinite products. And so you invoke this result right here, or in this form. Since it's two infinite products, you can choose the variables a and t so that the infinite product becomes the infinite series, and the infinite series, the infinite series becomes summation m greater than or equal to 0 of c over b q sub m, b q to the n raised to the mth power divided by q sub m. And now you interchange the order of summation. I won't go into detail about what's necessary analytically in order to guarantee absolute convergence to allow this exchange. It is, the conditions are not difficult to determine. And so we now have bq infinity over cq infinity summation m greater than or equal to 0. I'm bringing out everything involving m that doesn't involve m. And now I have summation n greater than or equal to 0 of a semicolon q t q to the m raised to the nth power divided by q sub n. And now this becomes another instance of this series that we have right here, either this one or that one. And so we can now write that expression in the circle as another infinite product. So this is bq infinity, cq infinity, summation m greater than or equal to 0, c over b q sub m, b to the m, q sub m. And now what is the infinite product? It's a t q to the m, q infinity, divided by t q to the m, q infinity. And now I utilize this identity that I had relating finite products to infinite products, and I can rewrite this as a thing with the finite products back in. Summation over m greater than or equal to 0, c over b q sub m, b to the m, q sub m. This is a t q infinity divided by a t q to the sub m, and the denominator is t q infinity and t q sub m. And now if you factor this out and that out, you see that you have precisely the expression that I wanted to show you. So this device, this classical device, Ramanujan was extremely clever at utilizing. So in his last letter to Hardy, Ramanujan states right at the beginning of his discussion of Mach theta functions that there are certain series in Eulerian form that are what he calls theta functions, or what we would now call it, we more likely in commenting on it, called modular forms, that have this closed behavior near the boundary, the natural boundary of the function. And the first thing that he writes down, which he calls equation A, is this summation n greater than or equal to 0 of q to the n squared over q sub n squared. And this is equal to the famous Euler infinite product, which generates the partition function. And of course, Ramanujan was extremely interested in and involved in probably the most famous paper that he wrote with Hardy was the paper on the exact formula for P of n, the number of partitions of n. And in this paper, he and Hardy discuss a number of approaches to finding this formula. And in particular, they do a study of this particular infinite series related to this infinite product. And so Ramanujan was very familiar with this, and certainly by the time he had returned to India in 1919. And in looking at series of this nature, one of the things that he seemed most interested in was applying techniques like we just saw for the Heine series. But this series, if you wanted something to work with this series, what you need is something that looks like this. And sorry, I made a mistake there. They're q squareds in the infinity in this denominator. Consequently, what he would like is a series that has this sort of factor in the denominator. And so just to mess around with this to see what might be possible, he will look at this greater than or equal to 0, put in q to the n squared, q sub n. I'll write it out twice. And what he does is to multiply numerator and denominator by this finite product. Well, look, what is q sub n times minus q sub n? It's equal to 1 minus q squared up to 1 minus q to the n. And then next one is 1 plus q squared, 1 plus q to the n. And now you can combine terms. This one and this one gives you 1 minus q squared. This one and this one gives you 1 minus q to the 4th, et cetera, et cetera. This one and this one give you 1 minus q to the 2n. So that this product is q squared sub n. And so that expression is equal to the summation n greater than or equal to 0 of q to the n squared. You combine these two, and you get q squared sub n. And now you're left with minus q sub n and q sub n. Well, even a much lower mathematical ability than Ramanujan sees that now this expression here is very much like what you see right there. And so if you are familiar with the Heine technique, you can change these into infinite products and see what happens. And so you proceed then as follows: n greater than or equal to 0, q to the n squared. You have q squared sub n. Here you have minus q infinity over minus q to the n plus 1 semicolon q infinity in order to get the top thing. And the bottom thing will be just very similar, q infinity and q to the n plus 1 semicolon q infinity. So we're now ready to deal with this precisely the way we dealt with Heine, namely we bring the products out front that don't involve n, and we expand these in the series using this original formula that was right here. that was due to Cauchy, or indeed goes back before Cauchy, but we know Cauchy had this. So this would be the summation m greater than or equal to 0 minus 1 semicolon q sub m, and then q, minus q to the n plus 1 raised to the mth power divided by q sub m. So far this doesn't look terribly fruitful, but we proceed as Ramanujan did often, just to see where something would lead. If one examines his lost notebook, you see countless pages where he is just calculating things to see where they go, and probably not a majority of pages, but a large number of pages in the lost notebook are just these sorts of calculations without any final result, although the things I'm doing this morning do not appear in the lost notebook. So what's the game? We bring the M series out front and bring out front everything that involves M. So we have minus Q to the M, and divided by q sub m. And now we have this sum, n greater than or equal to 0 of q to the n squared plus nm divided by q squared sub n. And this Ramanujan can now write as an infinite product, harking back to Euler's theorem, to use special cases of that in order to get the result. And so minus q infinity divided by q infinity, summation m greater than or equal to 0 of minus 1 q sub m minus q to the m and q sub m. And this will be minus q to the m plus 1 semicolon q squared infinity. And now you may think he's hit a real snag, because this product, you can't break it down into the finite product and the infinite product, because as it stands, because you need to know the parity of m. If m is even, this infinite product will have only odd exponents, and if m is odd, it will have only even exponents. So what one does is to break this down into two infinite series depending on whether m is odd or even. So the first one is the summation m greater than or equal to 0 minus 1 q sub 2m. Since m is even, the minus sign goes away. You have q to the 2m, and you have q sub 2m. And here you have minus q to the 2m plus 1 semicolon q squared infinity. And now, when m is odd, that minus sign is there permanently, so I'm going to bring it out front, and sum m greater than or equal to 0. The subscripts are now all odd. And the infinite product is now minus q to the 2m plus 2 semicolon q squared infinity. Well, you might start to feel that maybe things are getting a little out of hand, but Ramanujan would have been intrigued by this, because now at least he can pull this infinite product out utilizing this fact that we had right here, because the exponents on q in the first case are always odd, and in the second case are always even. And so we can now get one more step here. Here, the minus q squared comes out front. Summation m greater than or equal to 0, minus 1 semicolon q sub 2m, q to the 2m, q sub 2m, and this will be minus q squared sub m, minus, sorry, bringing out front the minus q squared infinity, summation m greater than or equal to 0 of minus 1 q sub 2m plus 1, q to the 2m plus 1, divided by q sub 2m plus 1, and it will be minus q squared sub m. Well, notice that we've gone from this very simple beginning into this, what seems like a mess. But there is enough intriguing stuff going on here that one would carry it another step further, and namely, look at minus 1, look at this expression, this quotient. Minus 1 semicolon 2m divided by minus q squared sub m. This is equal to 1 plus 1, 1 plus q, 1 plus q squared, 1 plus q cubed, all the way up to 1 plus q to the 2m minus 1. And the denominator is 1 plus q cubed, all the way up to 1 plus q to the 2m minus 1. All the factors in the denominator appear in the numerator. And so this becomes minus 1 semicolon q squared sub m. Similarly, minus 1 q sub 2m plus 1 divided by the minus q squared sub m equals the same sort of cancellation takes place, except now all of the even terms drop out and you have minus 1 semicolon minus 1 semicolon q squared sub m plus 1. As a result, the expression that you wind up with here is minus q infinity, q infinity, q semicolon q squared infinity, summation m greater than or equal to 0, minus 1 semicolon q squared, q to the 2m divided by q squared sub m, and q semicolon q squared sub m. I have broken this product here up into the odd terms, which are here, and the even terms, which are there. This equals 2 times minus q squared sub m. So I will write the second expression as minus 2 q squared minus q squared infinity, summation m greater than or equal to 0 of minus q semicolon minus q squared sub m, q to the 2m plus 1 divided by q squared semicolon q squared sub m, and q squared sub m plus 1. And now I want to point out to you, so at each stage, one might lose heart, except that something new happens at each stage that gives one hope. So what has happened to give one hope? What has happened is that this formula is now applicable to both the series that you see there. In other words, if you take one of the A or B equal to 0 and replace Q by Q squared, each of these becomes an instance of that formula. So let me just give you one example. So I have to apologize for this being so far down in the weeds, but what I really wanted to illustrate by it, as I hope you've seen, is that techniques that Ramanujan was familiar with are all extremely familiar with and good at, are all that you have seen me apply up to this point in this talk. And at each turn of this, you see what you have is an instance of something like the Highness series. So for example, the summation m greater than or equal to 0, let us just look at this one term. Q squared sub m, Q semicolon Q squared sub m. This is the instance of the of Heine, although I will carry out explicitly how this would go so that you could see that Ramanujan would do some more steps here. -1 Q squared sub m over Q squared sub m, Q to the 2m, and this would be my Q semicolon Q squared it would be Q to the 2m plus 1 semicolon Q squared infinity. You will now expand this as the summation n greater than or equal to 0 of Q to the n squared plus 2mn divided by Q squared sub m. And then you sum on the m series, and now, rather than dragging you through more of the weeds here, let me point out, then you sum on the m series. And what turns up is, after all that's said and done, you have Q squared infinity, minus Q squared infinity, Q squared infinity, and you have a very nice simple series, summation n greater than or equal to 0 of -1 to the n, Q to the n squared over minus Q squared sub n. And this is one of Ramanujan's Mach theta functions. The other sum, which I will not have time to go through, namely this sum, will yield, with some infinite products out front, it will yield summation n greater than or equal to 0 -1 to the n Q to the n squared divided by minus Q semicolon Q squared sub n. And this is the Mach theta function he called phi of Q. Bruce and I, in editing the Lost Notebook, put a 3 to make clear it was a third order Mach theta function. This he called psi of q. Bruce and I put in 3 phi of minus q because, and this is psi of minus q. And once everything is simplified, the above effort yields the following formula, namely q infinity divided by minus q squared infinity equals phi 3 of minus q plus twice psi 3 of minus q. In other words, and let me write down phi 3 of minus q is this series. And psi 3 of minus q is this series. All right. Now, this I believe is the aha moment. Because the left-hand side, Ramanujan would call it classical theta function, or indeed we would not only call it a modular form, it can be easily written as a quotient of instances of Dedekind's eta function. So it's an eta function product. In other words, it's a lovely, beautiful classical modular form with all of the concomitant lovely properties related to a modular form. In particular, it's the behavior of the left-hand side near the unit circle has this lovely closed exponential form, so that besides this particular exponential aspect of the singularity, all of the error terms are vanishingly small. And this occurs close to any root of unity of the form e to the 2 pi I h over k. What about the right-hand side? Say, what happens near, sorry about that. What happens near the q tending to I, the square root of -1? Okay. Well, when q tends to I, or let me make it easier than that. When q tends near q going to -1, when q goes to -1, phi 3 of minus q tends toward, it's necessary to do a careful mathematical analysis of this, but each of those forms is 1 plus q to an even power. And if it's 1 plus q to an even power, it goes to 2. And so the phi sub minus q does not blow up at all, but goes to a finite value, namely the sum of this infinite series, which is 2/3, I guess. Whereas psi 3 is singular, because when you put in -1, every single term in the denominator of each term blows up. And so what is the behavior of this near -1? This is going to a finite value, and this behaves exactly like that. In other words, this particular function behaves exactly like a modular form at this particular root of unity. Well, in effect, if you have what are called the even roots of unity, then this will stay finite, and this will blow up. If you have what are called the odd roots of unity, then this will blow up and that stays finite. In other words, he's found these two functions that have this crazy behavior. Half the time they act exactly like modular forms in all of their elegance, and half the time they remain constant. Okay, so that all of a sudden he knows these two functions are really, really special. And now what one needs to do is to go about seeing what other things can be done of this nature. Well, the next thing that can be done, and I'm getting toward the end of my talk, so I want to summarize quickly, but the next thing that can be done is, instead of this series, write that same series with what f3 of q equals the summation n greater than or equal to 0 of q to the n squared over minus q sub n squared. You can go through exactly the same operation up there. You will relate f3 to phi3 and psi3, and now you will be able to pick out the behavior of these functions at any root of unity, and you will have always this quality that half the time they behave like modular forms, and half the time they behave like that they attend to constant values as you approach the unit circle. He was extremely impressed by this, and indeed most of his letter, the descriptive parts of his letter to Hardy, are describing, in effect, what strange functions must be that behave like this. But and once you've dealt with that, the second function that he wrote about in his letter was the one related to the Ramanujan identities. And this, of course, is open clearly to what eventually is called f0 of q equals the summation n greater than or equal to 0 of q to the n squared minus q sub n. And the same game that we played above will lead you to the fifth order Mach theta functions that Ramanujan found. So it is my belief, let me summarize, that this series A, which Ramanujan knew very well and knew the importance of it, was something where he would, just to see what happened, try the methods of Heine to transform this. And there's really only one procedure that can work, and Ramanujan, being the genius he was, it was not too hard for him to figure out that this is the procedure that would work. And once there, he would be off to the races, and finally winding up with this formula that we saw right toward the end, namely this formula right here, which so clearly has this absolutely stunningly amazing quality, and thus would lead him on the path to finding all of these functions. But it is clear that he was enmeshed in these, what he called Eulerian type series, and was consequently able to work with them certainly as effectively as I have this morning, and without surprise may well wind up with this sort of theorem. So there, I think that covers everything. I thank you for your attention, and thank you for inviting me to participate this morning.
Okay. Arvind?
Can you hear me now? Thank you, Professor Andrews, for a wonderful talk, giving us a sense of how Ramanujan might have discovered the Mach theta functions. Questions from the audience? I don't see any raised hands.
So
Please go ahead.
Hi, George.
Hello.
Why,
Yes.
from your point of view, I mean, I know from modern point of view, would he examine the behavior near the boundary as the most important thing for the function? Just
I would think that would go back to the fact that that is what was crucial in the collaboration with Hardy in order to find the exact formula for P of n. The fact that the Dedekind eta function behaves beautifully near the unit circle and near all these rational the roots of unity, the fact that it behaves that way is what allows one, from the way they approach the problem with their using the circle method, to do this, so that he would realize from that collaboration that that is the extremely important part of this functions like this. If you look, so to speak, in the appendix of the paper that he wrote with Hardy on P of n, you'll see that they talk about other modular forms or classical theta functions where this same behavior near the unit circle allows similar expansions, similar exact formulas for the coefficients in the power series to be computed. So this is something that would definitely have been on his mind, I believe, from his work with Hardy on the asymptotics for P of n.
And just to be clear, I mean, Hardy and Ramanujan did not give the exact formula. I guess Rademacher and Selberg did, but
well,
are you rewriting history here?
It wasn't the exact formula, but basically it got screwed up because Hardy replaced the sinh of x with 1/2 e to the x. And so Rademacher and I believe Selberg.
Yeah. Okay.
Ramanujan had it right, but Hardy made him do it wrong.
Selberg makes a big point of this, that Hardy led them astray.
Yes, he does. Yes, he does. Exactly. But nonetheless, even doing it slightly wrong, nonetheless, the way that they get the formula is through the fact that at the roots of unity, the Dedekind eta function behaves in this very beautiful way.
Right. Okay, thanks.
Are there any other questions? Please go ahead, unmute yourself and ask. Okay. If there are no further questions, let's thank the speaker again. Professor Andrews, thank you very much for a wonderful talk.
Good.
We reassemble at 8 for the public lecture, right?
Yeah.
8 p.m. Indian Standard Time.
Thank you, Arvind and George. You have to log into another link for the public lecture.
Yes.
It starts at 8 o'clock. It's not the same link. Please note that.
Yes.
Thank you.